Right, today we're finally considering, after all this preliminary discussion, a theorem about point vortex dynamics in solutions of the Gross-Pittievsky equation in 2 dimensions. And I forgot to write here again the Neumann boundary conditions. Okay, and these are the basics. And so, okay, and so then we want to prove a theorem about vortex dynamics. We have these tools. The first tool, let's call it localization. I never really gave it a name. And so it says that the vorticity under reasonable hypotheses is very sharply localized or concentrated around certain points. Okay, and then the second tool, well, so we introduced these this notation. This J star is the sort of perfect velocity field, say the Euler velocity field, incompressible, with point vortices given by this sum of delta functions omega, the sum of delta functions omega, and with tangential flow along the boundary. And then using that, we can define the energy of sort of a renormalized energy for configuration vortices. And I asserted that this energy coincides up to some constant gamma, which is some number, coincides with the, okay, so there's a epsilon here, but it coincides with the natural Gross-Pittievsky energy for a wave function for a solution to the Gross-Pittievsky equation with vortices at these certain points. Okay, and so the second theorem says, okay, we have, if we want, we have explicit formulas for this velocity field, this so-called renormalized energy, and this psi star, which is roughly speaking an energetically optimal wave function on an epsilon scale with vortices at the given locations and the given degrees. I don't know if we'll need these. These are expressed in terms of the fundamental solution for the Laplacian, which can be written in terms of logs, and this so-called this thing, which is the regular part of the fundamental solution, sometimes called the Robin function, I believe. Okay, so then we have results saying that if the vorticity is concentrated near some points xcm, then the energy is essentially, not only is it bigger than the energy of this nearly optimal wave function psi star with vortices at those locations, so it's bigger up to a small error, but also it controls certain norms of, so if the energy is nearly that of psi star, then in fact psi is close to psi star in the sense that these quantities are small. Okay, and so those are the theorems, and then let's see. With that, we wanted to prove, and so this is our main result about point vortex dynamics. We consider a solution of the Gross-Pittievsky equations, and we assume that the energy is concentrating around certain points, say a little m0, and that this says the second assumption is that the energy is, roughly speaking, is asymptotically as small as possible given the vorticity concentration that we've assumed above. And so then we define a m of t to be the solution of the what we want to show is the limiting equation. So this is exactly the point vortex dynamics, the equation for point vortex dynamics with initial data given by these points a, m0. Okay, and so the conclusion is that the vorticity at time t converges to delta functions at the points given by the ODE trajectories by the point vortex system. Okay, and this is a theorem from around the late 90s. Since then, there are little improvements, but and so the improvements would say for finite epsilon, if for epsilon small enough, they would say they would give an estimate of the distance in the flat norm between this vorticity of psi epsilon and the trajectories given by the ODE. So there are so-called quantitative results that give stronger estimates. But one thing that there is not, that hasn't been done in the last 25 years, is to relax this very strong assumption. And so all these results require that the energy be extremely close to optimal, given the given information about the vortex locations. Okay, so that's the theorem. And we started the proof, we started discussing it. Here I'll present, let's give an outline. So here's the plan of the whole proof. And so the first claim is, and so I should be able to prove hopefully the first 4 of these today, and then we'll do the last one on Monday, and I hope have time also for some other discussion. Okay, so the first claim is, so here psi epsilon is always a solution satisfying the both hypotheses, and okay, and so the first claim is, so here I'm comparing the vorticity of the solution of the Grosbeck equation at time t to the delta functions at the initial limiting vortex locations. And so by assumption, when t is 0, this quantity converges to 0 as epsilon goes to 0. And the claim is that for some interval of time, and for sufficiently small epsilon, the vorticity in the solution. So what this is saying is that the vortices don't, there's some interval of time in which the vortices don't move very far from their initial locations. That's what this first claim is, sort of in words. But the significance of this is that this was the main hypothesis for the first theorem, the localization theorem. The theorem says, if exactly it had the same factor of rho sub a over 10, said that if we have some wave function psi, and we know that the vorticity of that psi is close to a bunch of delta functions where closest means relative to the minimum intervortex distance. That's what this rho sub a is. If that's true, and if we control the energy, then in fact, the vorticity is very sharply localized around some points xc1 up to xcm. Okay, and so so theorem 1 makes an assumption like this, and makes an assumption of the energy, and the energy assumption will hold always for all times because of conservation of energy for the PDE and our assumptions about the initial energy. Okay, and so once we have claim 1, then we know that for times up to time t naught, we can always find some points xc1 up to xcn such that the vortex is really localized around these points. Okay, first thing. Then with that information available, we'll be able to argue that, and so henceforth I'll restrict my attention to times between 0 and t naught, to times for which claim 1, to values of t and of epsilon, for which this claim 1 holds, and so for which theorem 1 is, for which I can appeal to theorem 1. Okay, and so in this range of t and epsilon, I claim that, so if I have an s and a t who are both between 0 and t naught, and I compare the vorticity at time s and the vorticity at time t, the claim is that I look at the flat norm difference, and that's going to be bounded by a constant times t minus s. And so this is up to small errors, up to errors that vanish as epsilon goes to 0. And so what this is saying is that it's a kind of a Lipschitz continuity. If I ignore this, which I'm entitled to do since I'm going to send epsilon to 0, if I forget about that, then this says that these functions are, if I think of the map taking t, the time t into the vorticity of the solution, the vorticity omega of the solution psi epsilon at time t, these functions are Lipschitz continuous. If I think of those functions from the time axis, from the a copy of R corresponding to times, into some space of measures or whatever with this F topology. I have a uniform, a Lipschitz continuity estimate which is uniform in epsilon. again, up to these small errors. These errors, epsilon to the alpha errors who are negligible as epsilon goes to 0. So if you like, this says that these functions which take t into omega of psi epsilon of t, this is a sequence of functions indexed by epsilon, functions from time into some space of measures. These functions are equicontinuous, modulo vanishing errors, equicontinuous in a certain weak topology. Okay, and so then claim 3 is, and this will be an easy corollary of claims 1 and 2, and I even almost discussed this last time. So claim 3 is that with claims 1 and 2 and earlier stuff, we'll argue that I want to find a subsequence epsilon sub k tending to 0 and Lipschitz continuous paths, so that for every little t between 0 and t naught in this time interval I found, I want to have, I'd like to have conversions of the vorticities for every t to a limiting measure. And the limiting measure is the sum of delta functions located at these points b sub m of t, where these paths b sub m are Lipschitz continuous. Okay, and so remember, my goal in the theorem is to show that my goal is to prove exactly this statement, where I have the additional assertions that the paths b sub m t are not just arbitrary Lipschitz paths; they're paths I find by solving the system of ODEs displayed above, the point vortex ODEs. And so the first milepost is to actually find some limit, and then we want to verify that these limiting paths b sub m of t are actually the paths a sub m of t that we find by solving the ODEs. Okay, and so the first step, and so you can see the final step is exactly that. I will prove an estimate like this. So I want to conclude that AM of t is equal to BM of t for all time t between 0 and t naught. And if I can do this up to some time t naught, then I can start at t naught and do it again, and I can extend it until the first collision, for example. I can extend it as long as the paths stay away from each other. Okay, so then having found these limiting paths b sub m t, I'd like to identify them with the paths that I get by solving the ODE. And so if I can, that will follow from this last estimate, claim 5. If I can do that, in order to do that, we need one more ingredient, which is we need to say that, okay, I'm gonna do this thing that analysts do that you may find disconcerting. I probably done it before already. In claim 3, I found a subsequence epsilon sub k tending to 0. I'm going to drop the subscript k and just write epsilon, and I'll forget it's a subsequence. But this this is harmless. You see, in the end, I will identify. I'll show that the limiting paths have got to be these ones coming from the ODE, and then it's easy to see that the whole sequence converges, not just the chosen subsequence. So whenever I have a subsequence with conversions in the above sense, then the limit we'll see a posteriori. The limit has to be the limiting paths have to be the ones coming from the point vortex ODEs. Okay, and so the last ingredient is, well, I claim that these so J is this conserved quantity, the momentum density or the supercurrent, that these are converging weakly in LP of dx and dt. So I look at the time interval from 0 to t naught, and these are converging to exactly the perfect current. So at time t, the limiting current will be the ideal incompressible velocity field generated by vortices with by vortices at the paths I find by this limiting procedure. And so I pass the limits. I get not only vortex trajectories, but I find that when I take this weak limit of the currents, I get the J star corresponding to those to the trajectories I found. Okay, and I'll need that to compare the paths found by this limiting argument. and the paths found by solving the ODE, which I'll do probably on Monday. Okay, so let's go through this. And so okay, let's get started. One point is claim 1 and claim 2 will end up being kind of, the argument will be very, very similar. So, okay, let's do what we can. And if I wrote this out, we wouldn't have time to get through it in the next day and a half. So I'm gonna have to go quickly. Okay, so here's claim 1. I've rewritten it at the top of the page. There it is. And okay, I want to start by stating a corollary of theorems 1 and 2. Theorem 1 is the localization theorem, and theorem 2 is the one that describes this energy. It says that the energy of psi, well, it says that psi is close to psi star if the energy of psi is close to the energy of psi star. And this is sort of refined lower energy bound. Okay, so here's the corollary. And so I want to assume these are the hypotheses of theorem 1. And the conclusion is, let's draw a picture. So the hypothesis is roughly speaking that there's some vorticity in balls around each of these points. And the conclusion is that if I cut out slightly larger balls around each of the points, and so I guess there's some smaller balls. And so I assume that there's some vorticity in the smaller balls. And the conclusion is that if I cut out slightly, if I look on the complement of slightly larger balls, balls of, say, radius rho sub A is always the inner vortex distance, is always a lower bound for the inner vortex distance and the distance to the boundary. And so these balls will always be disjoint and will always stay away from the boundary. If I cut out somewhat larger balls, then on the complement of those balls, the energy is just bounded. It's bounded by things involving, you know, I could write down if I wanted to some dependence on this constant and this, and maybe this, but it's bounded. And so what this is telling me is that the energy can only blow up sort of near where it's originally concentrated. Okay, how's the proof go? Let's see. I'll just sketch this. Okay, there's the picture. And so the proof says that under these hypotheses, so this is what theorem 1 tells me. Okay, if epsilon is small enough, this is true. And so then what? And also I can see, say, I believe this is true because you see by comparing, well, okay, let's write this. It's less than. Sorry, I'm doing this backwards. So what I want is okay. Okay. What I wanted to say that this sum of Ci minus Ai is bounded by the distance in the flat norm of this di times the delta Ci minus delta Ai. And maybe there's there's some constants here to get right, but there's a pi inside of here. And there's a pi here. Okay, so and here there's a 5, I think. Okay, so the point is, just by calculations we've done before, the distance of the points is bounded by this flat norm distance of the delta functions. Okay, and then this distance here via the triangle inequality is controlled by the sum of this and the sum of that. And right, I add and subtract this vorticity of psi epsilon of psi. And so, okay, and so I find these points Xi sub I, and they're near the okay, they're near the original points, and the vortex is very sharply concentrated around these new points. Okay, and then I apply theorem 2 to the new points, and theorem 2 tells me that the energy difference between the energy of psi and the energy, sort of the optimal energy of something with vortices at these new points control certain norms of the difference between psi and this optimal thing. And so what those tells me are that in particular it says that psi is close to, psi is, say, within order 1 of this function psi epsilon star with vortices of the blue points who can only blow up at the blue points. And so and so what this implies is that this psi can have a divergent part, but it can only diverge near these blue points. If I stay away from these blue points, everything is bounded. Okay, and so this is the idea. So we apply theorem 1, and then we apply, let's look at theorem 2. Right, and so when I apply theorem 2, I would do it with the, well, I would have this, and this energy is very close to, this is basically E epsilon of psi star epsilon with vortices at their points A0. Because my assumption is that my sequence psi epsilon is basically energetically optimal given the given vortex locations. And the point is when I move psi, when I change the points A0 to this Xi, I haven't moved the points far, and so that changes the energy by a bounded amount. I can control this difference by looking at the explicit expressions if I want to. Okay, and so this in here I'm again getting this with these new sorry, this is right. This is the this is right. And so if I stay a certain distance away from these from the A naughts, then okay, the energy of this thing is bounded, and the energy of this is close to that thing. And so I just conclude see away from the points Xi, the energy of psi is very say psi is very close to the energy norm to this thing that we know explicitly, which and its energy is bounded. Okay, so that's the idea. We combine theorems 1 and 2 in this way, and we find again. Rough information about the vortex locations is sufficient, and rough information about the energy is sufficient to tell us that the if we stay away from the approximate vortex locations, the energy is uniformly bounded. Okay, so this is the this is an ingredient in claim 1. And so what do we do? So in claim 1, we're trying to say that for a certain time interval up to time t naught, we find some time interval in which the vorticity doesn't move very far. The vortices don't move very far. How do we do that? Okay, so in the end, I want to use the evolution equation for the vorticity, and here it is in integral form. Okay, and so I'm going to make a smart choice of test function phi and put it in here and get information out of it. And so what'll I do? So what I'll do is I'll take a test function phi who is I'll take a test function phi who is say linear in a certain ball around. So let's do this with a new color. So so phi will be linear. I don't know what here. In these regions with this color, and the support of phi is in some larger balls. So phi vanishes outside these balls. Okay, I'll take this test function and let me assume that in the orange set, not only is phi linear, but its gradient will be, of course, a constant vector in the set. And let's assume it's a vector of norm less than or equal to 1. I can imagine it's equal to 1 if I'd like to. And if I want, I can make each test function, I can make on each of these balls, I can make phi vanish at the center. Didn't mean to do that. I can make phi vanish at the center of each ball, and then you see it's linear on a ball of diameter with some rho sub a over 5. And then, so on the boundary of the ball, its maximum height will be of order rho sub a. Then it goes down to 0 in order rho sub a. And so the gradient will be of order 1. It goes from, and then the second derivative will be of order 1 over rho sub a. It goes, the gradient changes. The gradient changes by an amount of order 1 and a distance 1 over rho sub a. Okay, so in distance rho sub a. So we can arrange it for this to happen. Okay, and then let me define T sub. So what I want is to show that the vorticity of the solution psi epsilon remains close to where it started. Remains smaller than this for a certain interval time. And so let's say T sub epsilon is the first time when my inequality fails. And so up until then, the condition I want is satisfied. And so my real goal now is to prove a lower bound valid for all small epsilon, a uniform lower bound for this T sub epsilon. Okay, and then I will have shown that, I will sort of trivially have shown that this quantity is less than rho sub a over 10 for times or for some uniform interval from 0 to t naught, if epsilon is small enough. Okay, so our goal is to obtain a lower bound for t, a uniform lower bound, uniform in epsilon. Okay, and so the way I do this is exactly as said here. I'm going to use the identity for the evolution of vorticity. And what happens when I do this? Let's go down here. Well, okay, I can see first of all the second derivative of this test function phi vanishes in the region where the functions are linear. So it vanishes in a ball around each point a0m. And in addition, it clearly vanishes off the support. And so the second derivatives are supported in these annular regions. Let's do it here. So the this is the support of the secondaries are these angular regions, and in particular, they're bounded away from the from this Azer, and they're in other words, they're right. They're contained in this set here, where I can appeal to the earlier lemma to estimate their argument. So they're a distance rho over rho sub a over 5 from the centers, and out there I've well, let's see. Let's take a look. Okay. So here's the logic. For times after time t epsilon, I can appeal to this above. I can for times after time t epsilon, this holds, and this always holds because by my assumptions on the energy and conservation of energy. And so for times after time t epsilon, I have this conclusion, and that tells me that okay. So when I integrate this, I'll get this is bounded by a constant, which is the second derivatives, the L infinity norm of the second derivatives. Here it is. Times the integral over the domain with the balls of rho sub a over 5 cut out. And then this is and this is bounded by well, you see this in turn is bounded by the energy. Okay, and so so what do I conclude? I conclude that this integral can grow at most, linearly in time, as long as the time is less than this t epsilon. Okay, and so I want to use this to prove that this inequality can't be violated. And the point is, well, also as long as t is less than t epsilon, then I know from above that. Okay, so this norm inequality involves taking this difference, the vorticity minus the bunch of delta function, and testing against an arbitrary Lipschitz test function, et cetera, et cetera. Here I've only shown that I've only controlled its growth when I test against a very specific test function. But I also know that for times up to time t epsilon, that this vorticity is very much like a sum of delta functions at some points c. And so if I know that, and I know that and I have this estimate for the restricted family of test functions I have, then I can say, then that's enough to conclude that for times up to time t epsilon, up to time capital T epsilon, this difference grows linearly in time, and therefore time capital T epsilon can't be too big. Is that clear? Should I write out in more detail? What do you think? More detail or not? It will take a second or two. Okay, this is bounded by. Okay, so the earlier theorem tells me that there are these points, these c of t, who approximate the vorticity very well. Okay, and this is bounded by. this is tiny, and this we can control. A constant times the integral of phi times this stuff for phi is above times. Okay, and so although and this in turn I can the point is I can basically treat this omega as being a sum of delta functions. I can swap it in and out, and so for some of delta functions I can control the difference of delta functions by a restricted class of test functions, phi, by iterating against a restricted class of test functions. Okay, so that's a little more detail. Okay, and that's how we prove claim one. And this is kind of a template for several arguments we'll do throughout the proof. We'll use this identity for the evolution of the vorticity. And the more I know about the right-hand side, about what the energy looks like, the more information I can obtain from this about how the vorticity is evolving. And so I'll refine in several stages my knowledge about these psi's using the ingredients we've established before. Okay, claim one, let's consider that proved. And let's go to claim two. And what is this? Okay, well, claim two is, here's what we're trying to show in claim two. So we've established this uniform time rule in which the vorticity doesn't move very far. And in particular, I can always appeal to my earlier theorem to assert that I have this nice localization. There are points who are kind of near, so in this time interval, it and so on, if there are points who are pretty near the starting point around which, at any time, I can find a collection of points around which the vorticity is very well concentrated. Okay, now I want to use that to show that the, to get this Lipschitz estimate on the vorticity. And so this is, the idea is, well, let's say, I don't know what T is less than S. So this is less than or equal to, again, I'm going to add and subtract. Okay, and this is like, as always, some very small number, epsilon of the alpha. And what is this? So this is exactly like claim one. Okay, so there my situation was I have this initial data. I know that at the initial data, the vorticity is converging, I know what the energy is doing, and that gives me control over the distance we move, in a certain time interval. And so essentially we would use the same argument here. We would take a little test function centered around the Ci of t and repeat the same argument. And this allows us to show that the vorticity at time s, that the distance it can move from the vorticity at an earlier time t is proportional to the distance as s minus t. Let me make a remark here. Oh, I see. This is supposed to be, somehow this got shifted down. So this was up here someplace. Okay, let me make a remark. And so in some way what we're doing here is we're estimating the vortex velocity. right? And I'm saying the vortex velocities are bounded by a constant. What does that constant depend on? The constant has a form, well, it has the form 1 over rho sub a, where rho sub a is the intervortex distance. And this makes sense because we know that the velocity field generated by a vortex is behaves like 1 over the distance in the vortex. And so if the vortices are close to each other, then they're subjected to velocity fields that scale exactly as 1 over intervortex distance. So that's this is a very reasonable estimate. And if we wanted to pay attention to these constants, they would all depend on this rho sub a. Okay, anyway, this is the same. So it's the same point. We sort of repeat the same argument. Then claim 3 is the we want to now use what we've done to find a subsequence such that the in this time interval, such that at every little t in the time interval, we want to find a subsequence and some limiting paths such that the vorticity here converges to the delta function support on the limiting path. So at time t, we get the vortices of b sub mt. Okay, so so I've sort of talked about this already. So first of all, so claim 1 tells us that in this interval from 0 to t naught, the hypotheses of theorem 1 are satisfied. Theorem 1 tells us that the conclusion is that the vorticity is very close to a sum of delta functions, a sum of exactly m delta functions. And so then very close in this flat norm. And so then it's pretty easy to see that the set of measures who are sums of m delta functions with coefficients plus minus 1, that's compact in any reasonable weak topology, for example, including this flat norm topology. This can be seen by either elementary or less. I mean, it can be seen by totally elementary arguments. It's like a point in a m-fold copy of this domain D. It's like a point in a finite dimensional space, basically. And so then by putting this together, we find that at any time t, the vorticities of the solutions if I look at those as a sequence in epsilon, those are precompact in this topology, and at any limit as I let epsilon go to 0 has this form. And then claim 2 says that up to these errors of order epsilon of the alpha who vanish as epsilon goes to 0, these functions are uniformly Lipschitz. So I said nearly because of the errors of epsilon of the alpha, but they're uniformly Lipschitz in this flat norm topology. And so some form of the Arzela-Ascoli theorem, some mildly sophisticated form, it's not that tough, we'll say that we can find a sequence that converges uniformly, which is the conclusion with respect to the same topology. And let me remark, this can also be proved by hand by basically repeating the, if one is at all uncomfortable with invoking the Arzela-Ascoli theorem in this setting, one can also prove this by hand by basically repeating the arguments of the Arzela-Ascoli theorem. We find a subsequence such that these vortices converge at a countable dense set of points, and then we use the equicontinuity to prove that they converge everywhere. Okay, so so at this point we have said we can pass limits at least on some time interval and get some limiting vortex paths, and they're Lipschitz continuous. What do we do next? So the next claim is that not only do we have limiting vortex paths, but the currents associated to psi epsilon have a weak limit, weak in say LP. I didn't say this, did I? I mean, so this is for any p less than 2, we have weak limits, and those weak limits are exactly what they should be. So once I find the limiting vortex paths, the weak limits are the currents associated with those vortex points. Okay, and so there's a part which I will not justify at all. This is the first part. Well, no, it's the second part. I guess we'll come to that in a second. So here's what we know. We know that for the subsequence, okay, I found a subsequence epsilon k. Now I'm not writing the subscripts k anymore. For that subsequence, the vorticities, so the vorticity is 1/2 the orthogonal gradient of this j, and so this nabla perp is 2 times vorticity, and we know that's converging in the this F topology to these delta functions supported on the paths that we found. We also know, and so I haven't yet used one of the main conservation laws is conservation of mass. Here it is. Right, here's conservation of mass. And what this tells me is that, well, the point is that this thing is very small in L2 as epsilon goes to 0. Remember, psi squared minus 1. If I divide by epsilon squared and integrate, if I square that, divide by epsilon squared and integrate, that's of order log epsilon. And so psi squared minus 1 is basically of order epsilon times the square root of log epsilon as epsilon goes to 0. Okay, and so then going back here, using that conservation law, so we're using it here not to get information about the time derivative, but about this thing, about the divergence, the divergence of the current by the conservation law is ddt of this thing, and this is the part who's uniformly bounded in L2 by conservation of energy, and then I multiply by this thing who's going to 0 very rapidly, and so I can see that this. What is this? I have some. If I have things who are uniformly bounded in L2, I differentiate, those will be uniformly bounded in H minus 1. And then I multiply by this decaying factor, and that will be converging to 0 in H minus 1. So the whole thing is converging to 0 in the H minus 1 norm. Not for every time, I have to integrate in time to take advantage of this time derivative. And so on the domain cross time interval, I can see that the divergence of the current is vanished. And so this is where I'm sort of recovering the Euler equation. The gross PDFC is not divergence free for finite epsilon, but in the limit as epsilon goes to 0, I get this divergence free condition only in this weak sense, weak LP dx dt. But nonetheless, I get divergence free, and that's crucial because we know from experience with Euler that's a vital property of ideal fluid flows. Okay, and so then we have that. And so here's the part which I'm going to not justify at all. So I assert that we also know, or one can also prove, that these quantities, the currents associated to the wave functions psi epsilon, if I look again in the space-time domain, in the domain across the time interval, and I look at that in some LP norm for p less than 2 as above, that I have uniform bounds. And so the situation is we know that these diverge in, or we expect these diverge in L2 because the energy is like, the energy is logarithmically diverging this log epsilon. But for every smaller p, in fact, they're uniformly bounded. And that means weakly precompact in the weak topology in LP in those, for those values of p as epsilon goes to 0. And so I'm just gonna assert this, but it's the similar ingredients to the proof of theorem 2, where information about the vorticity allows us to control what the energy is doing, and so I'm basically asking you to accept this. Okay, but once we do this, then what do? We have and so here I'm always considering a subsequence for which the vorticities converge to the paths I found above, and so then for the subsequence, we look at the corresponding currents, we get a weak limit. And from the above considerations, we find the weak limit satisfies the system of equations. We know what its divergence is, and we know that it's right. We know it's the orthogonal gradient is this delta function. So we basically know the divergence in the kernel, if you like, and we know the boundary behavior. And remember, these are exactly the equations that characterize the ideal velocity field. So J tilde is equal to J tilde at time t is equal to this ideal velocity field with vortices at b of t, and the degrees or integers never change. Okay, because this set of equations I've written down exactly characterize this thing. Okay, and so far we've just by some kind of compactness and by crucially using the equation for the evolution of the vorticity to control the velocity of the. So the crucial step was here so far. All this stuff that's illegible. Oh, I see. This was actually up here. I'm going to move this stuff around. So the okay, this was here. So we used the equation for the evolution of the vorticity to control, roughly speaking, the vortex velocities. That gave us equicontinuity that allowed us to pass the limits in appealing to our other results and find these vortex paths. And then we could go ahead and use the conservation, the law for conservation of mass to show that the limiting thing is divergence free. And then we know who it is. The limiting current, we know what the limiting current is. Okay, and so our task now is just to go back to here and use all this stuff to show that the limiting paths we found by the zoning procedure, in fact, coincide with the paths that we obtained by solving the ODE. And we'll do that by proving an inequality, by showing that the deviation of the paths that we found by this passing the limits, the deviation from where they're supposed to be. So this A sub m of t minus B sub m of t measures how far the path B sub m of t is from where we want it to be. This deviation is controlled by itself. The growth in deviation is controlled by itself, and therefore we can appeal the Grun's inequality and say that if it's initially zero, it remains zero. Okay, so we'll finish this on Monday, and that's it for today. All right, any questions about anything? And let me again, so I'm sorry it's sketchy. I hope this at least conveys the spirit of the argument. The key points are, well, we're using again and again this theorem 1 and theorem 2, which come from this vortex ball covering and from knowing this information, which really comes from calculus operations, knowing information about the relationship between the energy and the vorticity. We use that in a crucial way. And then we use this evolution equation for the vorticity, and we made exactly one. We only appeal to the conservation of mass once, but that plays this important role. We've done that, and we needed that. But the overall plan is to, by using this localization and these results relating energy and vorticity, to sort of increasingly improve our knowledge about how the energy is distributed, and then use that in conjunction with the vorticity equation to control quantities like this one. Okay, so let's put this in the chat. I'll upload this. And okay, and so there's just one argument left, and we'll do that. If that'll take, I mean, I'll go over it kind of quickly. I'll give the idea, but that'll take maybe 25 minutes, and that will leave some time on Monday to, I don't know what, not enough time, but so there's no real time for an overview, but to discuss, things, well, to mention things I didn't talk about, to talk about directions, open directions, etc., and to answer questions of any sort. Okay, any questions for now? What do you think? Hopefully this is not too, I mean, I'm rushing a bit, but hopefully you guys think of it. Yes, Lars?
I don't know if someone else has a question. I don't want to bother you to rush in all the time, but if not, I would have one very nice lecture. And I wonder, just a technical thing, how is it a difficult argument to say that the limit is necessarily like the sum of delta functions, the limit of the vorticity, or so that to rule out that you could have any other contribution that is not a delta, a Jerrard delta?
Yeah, so there are two things. So we know that the yeah, it's pretty easy. Okay, so the first claim is suppose for each epsilon, I have a measure of the form a sum of delta functions, say at most capital M delta functions with weights, if they're all, in fact, they're all, in my situation, they're all the same integers. And I want to argue that, so I have a sequence. So let's go back to the screen. Okay, so the okay, so my claim is so let's just say we have a I have a sequence like this depending on epsilon. So and so well, what can I do? I mean, so one thing I can do is I can choose. I can just look at the points in my domain to the M power. And so this sequence is pretty compact. If I can imagine, I can take the closure. This will converge to, so this converges after passing through subsequence of some C1 up to CM. So just in the sense of convergence of points in RM. And okay, so there's a little issue here, there's a potential for confusion. And so so one issue is these measures are invariant under relabeling. There's no meaning of the C1, the order has no meaning. And whereas the points in the domain to the M power are not invariant under relabeling. But nonetheless, so if so suppose I have delta functions, two delta functions, and their convergence some limit. I might make a mistake and call this one C1 some of the time for some epsilons and call that one C1 for other epsilons. It doesn't matter. I'll still get a limit, and so I'll just this will involve passing to further subsequences. So once I have a limit, so this happens. Once I have a subsequence, epsilon k, then it's easy to see that that these converge to something in the right form. So that's the elementary way of seeing it. There's a very if you like, this is an instance of a much harder and more general theorem in geometric measure theory, which says that if you have I don't know what, some kind of integral current satisfying whatever bounds, then a limit is again integral. But so this is true in much greater generality, but it's a harder theorem.
Thank you.
You're welcome. Okay. Yeah, so then let's just write this out. So you know, you can see this in the time it takes me to write it down. Okay, this is true for all test functions ci and so. And I forgot this sum here. Okay. So yes. Oh, is that a question? Let's see. There's something here. Oh, it's a, thanks. Okay. So
if I may, so you really make up for the fact that the vorticity is not, we don't have a transport equation for the vorticity by the fact that say we still got this, say, evolution equation for omega, and we have this very strong information coming from the say from the energy and energy concentration that tells us that these say these vortices cannot move too fast.
Yeah, that's right. And well, the final thing we have to do is to look at the is to get the PDE, or sorry, to get the ODE out of this thing. And so this plus, as you say, it's very strong information. It's got to yield the point vortex ODE in some way. That's what we have to do in the remaining step. Yeah, and that will turn out to be true, but it's not obvious if you just look at it. Yeah, but so indeed we have no transport equation, no Biot-Savart law. I mean, well, okay, in the limit there's kind of a Biot-Savart law. So the Biot-Savart law is what enables us to recover the current from the vorticity, and we've done that in step 4, so to speak, when we get this J star. But we still have no transport equation. The transport equation is sort of this vorticity equation here. That's what we have in its place. And so you see here, all we work with is energy and energy and vorticity. And so this is why it seems to be crucial for these arguments to have the energy, to have these very stringent assumptions on the energy. The energy is, as I said, roughly speaking, as small as possible. Whereas in the Euler equation, you never use the energy at all. You can have, you know, the energy can be divergent as epsilon goes to 0, because they have the Biot-Savart law, and so it's quite different. Okay. So all these guys are waiting for you to ask another question.
No,
if you don't have
I
any,
won't. Yeah, I'm sorry to bother everyone with.
No, it's fine. I think everyone appreciates questions. Okay, but anyway, I'll.
Yeah, thank you.
Oh, you're welcome. Okay, we've run out of questions for today, and so I'll bring this to a close.